Raising personal and confidential information is a critical part of providing efficient health and social care services. In order to operate effectively, we need to keep all of our information confidential, maintain its accuracy, and make sure it's available for use when we need it. Data breaches are becoming more commonplace. Malware, ransomware, spamming, and phishing are now big business. A successful attack on your organisation could cause a risk to patient safety as well as operational disruption and financial hardships. You are the first line of defence. You can help. It's important to remain vigilant.
So as you just saw. Hello. This picture itself entails a lot of information. Let's see. The dramatic first thing is that the dramatic surge in the cybercrime cost, predicting a climb from a $3 trillion in 2015 to an astounding $10.5 trillion in 2025. Although this is a prediction, but this alarming trend encapsulates a proverb saying well is dry, when the well is dry, we know the worth of water, highlighting the urgent need of robust cybersecurity measures before the cost becomes unsustainable. As this graph rises steeply, it reminds us that the prevention is better than cure. As you can see, these costs are worldwide and not just related to healthcare industries but across multiple other disciplines. To avoid such things or to prevent such things, companies across the world or cybersecurity companies across the world are spending billions of dollars every year, and they are compounding. The compounding annual growth rate is roughly around 20%, as you can see in the chart. Big companies like Cisco, Fortinet, Fujitsu, they have their own softwares in place to battle such cyber attacks. Cisco has SourceFlare and PowerFlare. Cisco paid like $2.7 billion to acquire these softwares, which have a throughput of 150 or to 300 megabits per second. Fortinet has 40 client its own VPN services. An industry-wide solution which is accepted is the software named SNORT 3. Now for the entire demonstration purposes, all the pink packets are clean packets. The blue packets without the red border are also clean packets. But the blue packet with the red border or the 0xZ packet is a suspicious packet which is in your network. Now let's see how Snort processes these packets. So for all the clean packets, it they go through multiple stages or multiple layers, and then the verdict is clean and they're sent to the network. But as soon as the 0xZ packet comes in, it goes through the multiple stages and the verdict is that it is a suspicious packet, so it is dropped on the spot. What is the problem which you see in this? It's too slow. It takes too much time. As I told you, that's not as a software solution which is based on top of OSI layers. Let's understand what the OSI layers are. So, packets have to pass through the complete OSI stack to reach the application layer, that is first node, to then process and again send the packets through the complete OSI layer, which is undoubtedly a big overhead which our processor or our proposed design does not have and is trying to avoid. Unlike processing in application layer, our processor does the packet processing or the packet matching at the data link layer. Now let us try to understand our processor design. Our processor has a pattern detection unit and an output queue. Now let's say this is an incoming stream of packets. The ping packet comes, the pattern detection unit determines that it's a clean packet. The packet goes and sits in the output queue. Such with every ping packet, and then these packets are sent to the network. Now, as soon as the blue packet comes in, our pattern detection unit might find out that these packets might be suspicious. But as soon as the 0xZ packet comes in, the pattern detection unit screams suspicious. It's definitely suspicious. So, now how will you solve this? To basically uh, to basically further our solution, we have integrated a general purpose processor which is dual core multi-threaded into our system. Now what this processor essentially does is it does pattern matching or signature matching for those packets. Now as you see that these packets in the output queue are then in the place in the memory bank where they are sent to either of the processors for a deep packet inspection. Now the processor then further determines that whether these packets are clean or they are suspicious. For all the clean packets which are actually fine, these packets are then further sent into the network, and for all the packets which are suspicious and now after the packet inspection it is confirmed that they are suspicious, these packets are sent to trash. Let us try to see what happens inside the pattern detection unit. The pattern detection unit is nothing essentially but it's a bloom filter. It's a bloom filter applied on a hardware. So basically what it does is it is a group of multiple hash functions which then do a bitmap matching and then essentially give a verdict. The verdict in the case of 0x dead is suspicious. Now why choose a processor, or why do you think, like, why shift from an industry given standard to a processor? One, it has a higher throughput. As the digital world will expand, the need for protection or the need for cybersecurity or the growth of cybersecurity itself will follow. From a trickle to flood, emphasizing the performance improvements from SNOT's 700 Mbps, which is 6 times. Our processor is giving you 6x better improvement. Not just that, but our processor is much faster. It has much lower latency. It is 2000 times faster compared to SNOT, which takes like 200 microseconds to do the job, which is done in less than 100 nanoseconds. Our entire processor design is fully pipelined and functional to 5 nanostages per pipeline stage. Now let us understand how we got this. SNOT rules are complicated, but most of them can be skipped or they can be very quickly skipped if a short pattern is seen. False positives do exist. As I told you, the blue packets without the red border they were determined to be suspicious by the pattern detection unit, but upon deep packet inspection, it turned out that they weren't suspicious. So false positives do exist. For that reason, we have general purpose processors integrated which further inspect the packets by a previously running software. Now, a very genuine doubt comes as this might slow things down. Yeah, there's a fair enough thinking that this might slow things down. But how often are you going to get a suspicious packet? 0.3% or even less than 0.3% is a chance that you might get a suspicious packet. Zero point 0.3 means 3 packets per thousand. The impact on performance due to this might actually be negligible. Now I'll pass on this presentation to my teammate Pavan.
So Utkarsh has talked about how uh, Bloom filter is acting as an hardware accelerator to detect patterns and to accelerate SNOT. I would be talking about the pipeline and I would be giving you a demo of our project. So the pipeline works in tandem with the Bloom filter to deep inspect the false positive verdicts that are given by the Bloom filter. And this is the architecture of our pipeline, of our processor pipeline. Ours is a 7-stage, 8-threaded pipeline. Uh, and we have an extra EX stage and we have an extra write back stage compared to a traditional 5-stage pipeline. And yep, I would be now giving you a demo on our work on the working of our uh, Bloom filter or SNOT, accelerated SNOT. This is my virtual machine and I would be connecting it to my FPGA nodes. This is my FPGA node and I would be loading my bit file into the FPGA. So I would do nf download fast router.prt. So bit file is loaded onto the FPGA. I would then do an RKD. Okay, ours is a reconfigurable Flume filter. So we've written. So I'll first show you show you the working of it, and then I'll get into some more details of the implementation. So we would first do we would first turn up a netcat server on one of these FPGA nodes. Yep. So let's do it on node number 0. I've turned up the FPGA server on node number 0. I would be starting my client on node number 3 that would be communicating with node number 0. We would be sending out a message called hello world. So you see this message passes, and now we will configure our Bloom filter, or we'll configure our hardware accelerator to detect a particular pattern. So we detect the pattern called, maybe, let's say, payload, and first we will check the match count, that how many. Okay, first we'll load it. So there we have written a Perl script for this that loads a particular pattern. So the pattern now is loaded. The Bloom filter for this is loaded, and if we check the match count, uh, count. Oh, this is the wrong command. Let me check the Perl script. Okay, it's just match. So the count right now is 0. We've used the NetFPGA register interface to have a match count inside our hardware accelerator. Uh, so now we pass, let's say, payload. It works. Payloads. It doesn't work. I mean, it doesn't pass through. So this was our pattern that we are stopping it from passing through. Payloads and patterns. You see, this doesn't pass. This passes. Malicious payload. This doesn't pass. This passes. And if we check the match count now, uh, we see the match count right now is 3. That means there are 3 patterns that match this particular Bloom filter that we've uploaded. And as I said, this is reconfigurable. We could upload, or we could put in many more patterns in there. So I would load in, let's say, so if we load in this particular filter, null.txt, this lets all the patterns pass through. Even this passes through. Even the even the payload called patterns pass through. And so this is the demo of this project. You see the appropriate packets that we configured that needs to be dropped is being dropped, and the packets that needs to be passed are being passed. I'll show you. So I'll just turn off this server for now. Okay. This is our Perl script that we are using to configure the patterns. We use a typical reg write and reg interface or the register interface given by netfpga write out patterns of the Bloom filter. So this makes it so now that we have seen the demo of the working of uh, a project that accelerates SNOT, this was our bandwidth comparison that we got. While SNOT at 8 gigabit Ethernet MAC gives you a throughput of uh, a lot less than 1 gigabits per second, while our system, the NetX PGA system, which is acting as a router, and with our hardware accelerator and our processor, we are able to achieve uh, a little more than 6 gigabits per second. Uh, so we see this solution is much more effective than the software-based solution called SNOT. So why shift to Emid? It's it's a performance boost, as we've seen in the previous slide, that it, even though it is not perfectly it doesn't perfectly detect patterns on a line rate, it it is close to that, and it's much better than SNOT. It's also far efficient because it doesn't uh, because these are all interconnected, and it's plug and play. We would be giving you all the softwares to interact with this. I think the major reason why a lot of hardware companies struggle with is not providing enough software solutions that make it more interactable. But our system is reconfigurable, and we give easy interfaces for users to configure it with ease. Yeah, this should be our demo video for our project uh, that accelerates SNOT. If there are any questions, please let me know in the comment section.